Hello friends. So today we are going to solve four questions, and these four questions will be from magnetic fields. So the first question, one second. Okay. So we are going to solve four questions, and four questions these are from the chapter magnetic fields. So in the first question, it states that a ring with the radius r carries a current I. Show that the magnetic field due to the ring at a point in the plane of the ring, a distance a from the center, either inside or outside the ring, is given by. So we would find out basically the magnetic field because of the ring in the plane of the ring, okay? And the distance from the center is given as a. And for that we can just draw an approximate figure. And so let us draw a ring whose center we say is at the origin, okay? And this is ring is in xy plane. So this is our x-axis and y-axis, and on this ring we consider a point P which is on the axis x. We consider point P which is at a distance of a from the center of the ring. So this point P can be represented as our a comma 0 comma 0. Okay. And in order to find out this magnetic field, obviously we are going to make use of the Biot-Savart's law. Okay. And so we consider a point, any point on this ring, and let us suppose join this ring, and this angle is supposed as theta, okay, and the distance between the ring and this point, and let us call this point as A, and this is our O, and so let us call this OA as our r prime theta. So basically we can say that this point A can be varying from 0, and as it is going to move around the circle, so we can say this theta is going to vary from 0 to 2 pi. Okay. So first important part is that we are going to define the geometry and the coordinates, and the coordinates we can define our own way, okay, because that is quite convenient for us. Okay. Therefore we can say that a circular ring of radius r we are having a circular ring and whose radius is our capital R, and it is centered at the origin. It is centered at the origin, and we consider a current element, small current element, by which is denoted by angle of theta. Okay. So we can say that a current element by angle theta, and this current element in this particular case is represented by point A. Therefore, we can write that our this r prime theta will be equal to, we can write its coordinates, and that will be our r cos of theta, r sine of theta, and 0. And this theta will be our less than 2 pi or greater than or equal to 0. So basically, because we have taken this point A at an angle of theta, at any angle theta, and if we want to form a ring, this theta should be varying from 0 to 2 pi. Okay. From here, we can find out the current element. So we can say the current element and let us suppose that current element is represented as our d of L. Then this d of L can be written as our d r prime d theta and times d theta. And so let us substitute value of our r prime, and this can be written as d of d theta, and we have our r cos of theta, r sine of theta, and 0, and this is our d theta. Okay. So we can just derivate it, and this gives us that the current element will be given as minus r sine of theta, r cos of theta, and 0, and it will be our d of theta. And we are given that this point P, on which we are going to find out the field, is in the plane of the ring, and the distance is given as a from the center. So we are given the field point P lies in the plane of the ring, lies in the plane of the ring. Okay. 1 second. And it lies in the plane of a ring whose at a distance a. At distance a from the center. Therefore, and for the sake of convenience, we assume that this point lies on the x-axis. Therefore, we can write this our coordinate for this point P, our distance with respect over from center. We can write this as a, 0, 0. Therefore, we can write that the vector form from our A to P. Okay, so we can just find out this distance. Okay. Therefore, we can say the vector from the source point r prime or A in this particular case to P. The vector form from, not from, the vector from A to P, and that we can write this as our R is equal to our R of P minus R prime of theta, and which gives us A minus R cos of theta minus R sine of theta and 0. And let's find out its square. So we can say our this R square, because it is our theta dependent, okay, or we can say the magnitude will be equal to A minus R cos of theta whole square plus R sine of theta whole square, and if you open the bracket we get this as our A square minus 2AR cos of theta plus R square cos square theta plus R square sine square theta, and this our R square we can take as common, so this will be cos square plus sine square, which will be equal to our R square. Therefore we can write that this is equal to over A square minus 2AR cos of theta plus R square, and therefore we can say that our R of theta, that is our basically distance, will be equal to over A square plus R square minus 2AR cos of theta square root. So this is nothing but our basically distance. Now we can use our Biot-Savart's law to find out the magnetic field. So we can say our Biot-Savart law, and this law gives us that the magnetic field of our D of B will be equal to, is equal to rather mu naught upon 4 pi, and it comes our I multiplied by the element, current element dl, cross product with R, and divided by our R whole cube. And for this particular question we can slightly remodify it by writing this R as a R of theta. Okay. So with this as mu naught 4 pi, and this is our I dl cross R, and in this particular case we can write this as R theta and whole cube. And we are mainly interested now, we have to find out the cross product dl cross R. Okay. So we already have them, dl cross R, so we can write this straightforward, that our dl cross R, and this is our x, y and z. So x is our minus R sine of theta, R cos of theta and 0, and this is our A minus R cos of theta minus R sine of theta and 0. And the cross product, obviously we know only z component is going to survive, And so we can write this as our dl cross r, only our z component, and d of theta will be equal to, this comes minus minus will be plus, so it comes as r square sine square theta minus r cos of theta times a minus r cos of theta d of theta. And only thing is left is to calculate the term which is inside the bracket. Okay, so we can write this will be equal to our dl cross r will be equal to our 0 comma 0, because only z component is left, x and y component are 0, and this will be equal to our r square minus ar cos of theta. Therefore, we substitute it and we are going to get the answer. So we get that a magnetic field, we are going to get a magnetic field because of the current element. We have to find out that for a complete ring. So we get our magnetic field is equal to mu naught I upon 4 pi, and this comes as our r square minus ar cos of theta and a square plus r square minus 2ar cos of theta and whole raised to power 3 by 2. Only our z unit vector direction is going to survive. X and y component both will be equal to 0. So this is our value of our magnetic field. That was our required. I think this is the required, or we have to solve further. Okay, so only difference is that we can integrate it because for the complete cycle, and we are going to get the answer. Okay, so we can say that the total magnetic field B will be equal to twice of our mu naught I upon 4 pi, and this becomes from 0 to pi, and r square minus ar cos of theta and a square plus r square minus 2ar cos of theta 3 by 2 our z unit vector times d theta. So this is our magnetic field because of a ring in a point, or at a point which lies in the plane of the ring, and the distance of that particular point is a. That point can be inside our ring as well as the outside of the ring also. Okay, so that was the basic question. Next question. Okay, so it states that consider a square loop with a current I. The side length is a. The goal of this problem is to determine the magnetic field at a point at a large distance r, with r is much larger than a from the loop. And this problem is quite interesting one. And in general, what we try to solve it, how we try to solve is that the point P is basically given to us, and this is very far as compared to the side of the square. Okay. So in general, what we do, or we assume that one of these sides are ideally parallel to this point P. This we make an assumption, so that the field because of these parallel sides are, we basically neglect them. Okay, but in you can say in general, if this point P is very far, very far, okay, in that case, these lines we cannot take them this as a parallel. Okay, we can just, because if they are very far, we can just, in ideal situation, we can assume that they are at an angle of theta with respect to this point P. So this way we get the exact relationship at the point P and with respect to the square field. Okay, so in the first case, what we are going to do, we are going to solve this question with the more traditional way by considering that these two parallel lines are exactly parallel with respect to the this r distance, exactly parallel. Then we are going to make an error correction. Error correction means, like I said, if this point is P is very far, we are going to assume that these side lengths are making an angle approximately at an angle of theta to the vertical, that is point P. Okay, that is going to give us a exact relationship or exact magnetic field at point P, specifically for the condition when this R is very much far than A. Okay, so we are going to do it in two parts. And so first, like I said, so let us mean this is our A, B, C and D. So in the first part, we are only going to consider the horizontal sides, that is our AB as our DC. Okay, we are going to ignore our AD and BC. In the second part, we are going to insert or calculate the magnetic field because of our AD and BC as well, and then we are going to find out the net magnetic field at point P. Okay, so this is okay. So let's start from our horizontal sides. And we know that our because of a Biot-Savart's law, we can easily find out, because this AB and DC are nothing but a straight conductors. Okay? And if they are each having a length A or at a distance r. Okay? So we can write a general formula for Biot-Savart's law, and then we can reformulate that Biot-Savart's law according to the given figure. So we can say that for a straight finite wire, for a straight finite wire of length A, at a distance r, at a distance r. Okay. Therefore, we can say that from Biot-Savart's law, the value of magnetic field can be approximately written as our mu naught 4 pi, and value of the current is given to us as our I, and the current element, that is our side length, is our A, and the distance is our r. So this becomes our r square. And in this particular case, we are having, let me clear these things. So we have this as A, B, C and D. Okay, so we can, from the figure itself, we can see that the side AB is much nearer to P as compared to DC. Okay, and this point, let us suppose our O, is at the center of this square. So obviously this will be equal to our A by 2. So therefore for side AB, we can write this as R minus A by 2, and for side DC we can write this as r plus a by 2. That's our distance. So we can say for horizontal side AB, for horizontal sides, and we start with our AB, and for AB we can write that our r, which is our distance, is equal to our r minus a by 2. And for our side DC, the value of r, that is our distance, will be equal to r plus a by 2. And like I said, that this point, our AD and BC are along the horizontal side, is nearly resulting in our only, we are ignoring it basically because they are parallel to the point P. Okay, these are basically parallel. And for that, for the first part we are going to ignore it, and then we come to our this second part, considering that effect. Therefore, we can revise our this equation number 1 as per our side AB, as per our side DC. Current is same, only the distance is going to vary. Length of our element, current element, is also same, that is our A. Only this R is different. Okay. Therefore, we can write that this magnetic field, because of the wire AB, it can be written as our plus mu naught upon 4 pi, and this comes as our I times A and R minus A by 2 and our whole square. Similarly, we can write this as magnetic field due to side our DC can be approximately written as our minus mu naught upon 4 pi, and this comes as our I times A, R plus A by 2 and whole square. And from this figure we can clearly see that the direction of the current in AB and DC are opposite. Okay, from AB it is flowing from B to A, and from DC it is flowing D to C. Okay. So one direction we take as positive, other direction obviously will be equal to negative. Okay. So it means that our net field therefore we can say that our net field, and let us call this as B horizontal because we are only discussing the horizontal parts, will be equal to, this comes as our mu naught IA upon 4 pi, and this comes as 1 upon R minus A by 2 whole square minus 1 upon R plus A by 2 whole square. And we are only interested, we can easily calculate this, the bracket part. Okay. And so we can sort it out, and we can say that our magnetic field, because of the horizontal parts, that is our AB and DC only, will be equal to our mu naught IA upon 4 pi, and we can take our R as common from both the denominator, so this comes as our R square, and this will be equal to 1 upon 1 minus A upon 2R whole square minus 1 upon 1 plus A upon 2R whole square. And we can solve it using by Taylor expansion, or our binomial expansion we can also use. And for that we assume a small parameter which is this is a dimensional parameter, this is epsilon, and this epsilon is equal to our A upon 2R, and this epsilon is much less than our 1. Therefore, we can write that our magnetic field, because of the horizontal parts, is equal to over mu naught Ia, and this is 4 pi r square 1 minus this parameter which is epsilon minus 1 upon 1 plus epsilon whole square. And we can expand this parameter and get the solution. Okay, so only difference between these two parameters, it is here is negative and here it is positive. That is the only difference. Okay, therefore we can write this as our 1 upon 1 minus epsilon whole square minus 1 upon 1 plus epsilon whole square. And this can be written as 1 minus epsilon minus 2 minus of 1 plus epsilon, and this will be also minus of 2. And from here, if you open it, that first part will be coming as 1 plus 2 epsilon. A higher order we can just neglect it, minus 1 minus 2 epsilon. And one second. Yeah. So this will be coming as approximately will be equal to over 4 epsilon. Therefore, we can write that our magnetic field, because of our horizontal part, will be approximately equal to mu naught Ia upon 4 pi r square times 4 epsilon. And we substitute value of epsilon, that is our A upon 2r. So this becomes as a mu naught Ia 4 pi r square times 4, and this is A upon 2r. And this will be coming equal to as our, we can just cancel out our 4 from here. So this comes as our mu naught I A square, and this comes as 2 pi r cube. Okay. And this is the magnetic field only because of our horizontal part, because we neglected the vertical portion. Okay. And so now let us consider our vertical sides. Vertical sides. Okay. And we know that our each vertical side is having a length A, okay, and this distance is approximately, we can say, given as our r. Okay. And so we can just, now we are only interested in the vertical portion. This was our A, B, and C and D. So this was center here and point P. Okay. So if point P is very far, so we can say this, the vertical, they are making the angle of theta. Okay. And so this was our, this distance will be over A by 2. And this will be equal to our r. But in this case, our this point P is very far, such that the distance of this point P is approximately equal to r. Okay. Therefore, we can just draw this as a right